Hello everybody, welcome to our video on endurance limit. So what you're going to be doing in this video is to calculate the effective endurance limit of ferrous material, and the book we're going to be using is Elements of Machine Design by Robert Mott. So what we'll do is we'll figure out, given the standard endurance limit for kind of a known condition, how we calculate the endurance limit for the particular part that you have. So what happens is any surface that you take actually tends to have a lot of defects in it. So there might be cracks, there might be other problems on it. So if you kind of like really zoom into one of the things and then we apply kind of like a sinusoidal, so it could be like if I have this material here, I can basically pull on it and then push on it like this, and then I repeat and kind of like keep reversing the load. This is known as repeated reverse load. So anytime a material is in tension, any cracks and defects tend to amplify. So essentially there will be kind of like a localized stress concentration. The effect might be really small, but then the damage accumulates over time. So when this happens, you'll notice that the crack will gradually grow, and then eventually what will happen is the crack will reach a critical stage, maybe at this point, where the entire material would suddenly fail as if it were a brittle material. So an example would be like if you take, this is a failed crankshaft that I found on Wikipedia. So this shows this darker region here, which is basically this darker region here was kind of like the slow initialization of the crack due to fatigue. And then all of a sudden in this area here, the crack would kind of propagate really quickly, and the entire thing basically fails as if it was like a brittle material. So generally what is done is we have a standardized testing procedure. This consists of kind of like a cylindrical member. So obviously I didn't get a metallic rod. And then there is kind of like, think about the spot here. And then basically you have a simply supported beam like this. So my fingers are basically simply supporting. That means the rod can kind of like rotate about this axis. So this is usually actually a bearing which kind of represents a simply supported case. So when this happens, so imagine there is a like a part here, and then what is done is you apply a load on this particular region here. So when this happens, and then you imagine there is a spot here, and then this is simply supported, and then this kind of is continuously rotated, and then notice that the spot goes to the bottom, and then it kind of comes back to the top. So when it's at the top, it's in compression. So this is basically like bending this way. So this part would be in compression. The spot here would be in compression. So when it goes kind of like a full 180 degrees, so it's kind of like right at the bottom over here, then the load will cause a tensile force here. So this wants to become larger, and then you kind of go one more circle, and this region wants to become smaller. So this would be a compressive stress. So this is how the testing is actually done. So this would be a repeated and reverse testing. So when this is done, this is actually done on a standard steel material. So it's usually wrought steel. So wrought basically means that it's been processed, either like machined and then ground and things of that sort. Like basically like higher processed steel, and usually a circular shaft of 0.3 inches diameter is chosen, and then it's machined and then like different combinations. So it could be machined, or it could be machined and then polished, and so on and so forth. So once this happens, you basically have like maybe like a set of millions of these rods or these shafts subject to different loads and based on different strengths, and then you can potentially calculate an endurance limit. But what is typically done is once you have the endurance limit, we basically consider the endurance limit as the mean. So anytime you have any distribution, so you're going to have like a normal distribution like so. If this is the any particular value, so this would be the SN, or the failure, the endurance limit, and this would be the number of samples. You're always going to have like a normal distribution like this. So what you do is you basically pick this mean value, and then that is reported as the endurance limit. So like the 50% case would be the endurance limit that you have. So any change from these materials, either if instead of the rod like nice steel, if you go to a different steel, then your endurance limit will be lower. instead of the 3-inch, if you basically pick a larger diameter, then there is an increased probability of fault. So if I have this shaft here, if it's become larger, so there's more material and then larger probability of faults on the surface. And then instead of it being a bending load, so instead of it being like rotating and repeated in reverse, like instead of it doing like this, if you're just like pulling and compressing it, that exposes a larger area to the endurance effect or the cyclic effect, so the strength becomes lower. So what you're basically interested in is, given the standard data, first, how do you actually determine the standard strength? So you wouldn't want to kind of like randomly figure this out. So there's basically a table that's given in the book which shows you the endurance strength for different ultimate strength material versus the number of versus the machining parameter. So the good thing about steel is that you can kind of like all the properties of steel can be determined by the hardness. So what is done is we can basically calculate the effective endurance strength Sn prime as Sn, which is going to be the standard that we get from the chart, times a bunch of correction factors over here. So this would be the correction factors which we'll basically discuss in the following slides here. So this would be the standard case here. So this is the figure 5.8 in both the 4th and the 5th version of the book. So if you look, what it basically plots is the tensile strength of the steel versus the endurance limit. So steel is kind of interesting that the basically the hardness of the steel kind of determines a lot of properties. So if you have a particular hardness, it will determine the endurance strength. It'll first determine the ultimate strength of failure, which is going to be the full strength when the part completely breaks, and then it also determines the endurance strength. So what is done is the wrought steel of different strengths right here is basically plotted, and then like different machining conditions. So the topmost is polished here. The surface is nicely basically first machined and then polished. The next one is ground, which is like one step lower than polishing. Then you have a machined, which is just like you take the material and like just machine it, or it's cold drawn. And then as rolled and as forged. So the material, as engineers, you typically use a machined part, but sometimes you might need to analyze a part which is you know, just like as rolled or as forged, which is kind of typically a rare case, but it's still good to know how to get those values. So excuse me. So what basically happens is, the better the surface is, like more processing, when more refined the surface, for example polished versus ground, the higher would be the endurance strength. Also, you'd notice that the endurance strength for the polished case over here is roughly half the ultimate strength. So if I pick a point here, so if I pick a point here 180 and then I go up here, so if I pick 180, so I go up, and then this point here would be roughly 90. So this is basically 90 over here. So this is basically the Sn, or the standard endurance strength, is roughly half the ultimate strength, and this is only true when the surface is polished. So for everything else, the strength tends to be lower, and then you would necessarily have to refer to this particular chart. So let's look at a really quick example problem. So for instance, if I tell you the calculate the Sn, or the endurance strength, for a material which has an for a steel which has an ultimate strength of 120 kilopounds per square inch. So KSI stands for kilopounds per square inch, and then we are going to be using the imperial units here. So we can quickly calculate this. Let me give you a minute to see if you can look at the chart and figure this out. Okay, so how do we do this? So we locate where the 120 is, which is over here, and then what we're going to do is we're going to draw a vertical line. So we have given the material type. So this is basically a machined part. So that will basically be here. So you locate the machined part here. We locate 120. So we draw a line from the 120 up to the machined line, and then figure to the other side. And then you need to look at the like the lines here. So each here between 20. This is basically 5, 10, 15, 20, and so on. So each line represents 5 units here, So this right here is 40, and then this would be about 42. So the ultimate strength would be about 42. And then again, this is basically kilopounds per square inch. So that's the unit here. So the first material correction factor we're going to look at, or rather the first correction factor we're going to look at, is the C sub m, or the material correction factor. So generally, the lower the quality of the material, the more likelihood that there will be faults and kind of like defects on the surface from where the cracks can initiate and the material would fail. So wrought iron is kind of a reference, which is kind of like refers to a worked or processed steel. For it, the Cm, the material C value, is said to be 1. Cast steel has slightly more defects, so the value is 0.8. Powdered steel is even less, because it's powdered and then you put it together, it's going to have a lot more defects, so we choose a value of 0.76. Malleable cast steel is 0.8, and so on and so forth. So these are found in the section 5.4 of the book, of both versions of the book. So you can basically look at that particular table, and then it will tell you these. The next correction factor we are going to look at is the type of stress factor. So basically, testing is done in repeated, reversed, and bending mode. So only the defects on the surface are important. So if I basically have this in bending, the top fiber over here on the outer rim is going to have the maximum tensile load. So if I basically take the same thing and then pull the whole member like this, like this, so the entire cross section area is going to be exposed to the same load. So what happens is there are more chances of defects actually occurring, and so we have a correction factor here, or the effective strength becomes even lower in axial tension. The value is taken to be 0.8. Keep in mind that when the material is actually in compression, the endurance doesn't, well, the cracks do not really like propagate or become larger. So we're not like super concerned. So if it's like completely compressive load, we're not really concerned about endurance per se. So the next thing we're going to look at is the reliability factor. So any distribution that you have, so you're going to have a normal distribution of the results. So basically, if I cross the Sn, the strength, and then this is the number of elements that I do the test for, I'm going to get what's known as a normal distribution, which kind of looks like this. I'm going to have some which have like very small endurance strength, some which is going to be significantly large. But what I'm really interested in is I choose the mean value over here as the representative strength. So what that basically means is about 50% of the samples that I tested, which would lie over here, actually have a strength lower than the reported value. So if I wanted to get a higher strength, basically I wanted to have a higher reliability, or basically if I say 50%, that means like 50% would potentially fail if I load it to this particular load. So if I wanted a higher probability of success, I'm going to choose a value over here, maybe use the yellow, or actually continue with the blue here. So I want it here, then what's going to happen is my strength is basically I've chosen a lower strength that basically ensures I have like a higher reliability. So if I choose this or as my design strength, I'm going to have less elements which have a lower strength and less likelihood of failing. So this is the idea behind the reliability factor. So this is basically given in table 5.2 of the new book and table 5.1 of the old book. So for a 50% reliability, you use a CR of 1, which is the reference value. For 90% CR is 0.9, for 99% it's 0.81, and so on and so forth. So you'll notice that each successive increase is more like a log scale, that there isn't, you kind of like almost linearly decrease the reliability. So you're going to have, if you need it like very, very high reliability, your strength kind of keeps going down, or the effective strength keeps going down. So the next thing we're going to look at is the size factor. So generally what will happen is the larger the diameter of the part, there is going to be like more locations in which the failure can actually initialize. So what happens is we need to correct for this or take a reference value. Since our reference diameter is 0.3 inches, the larger the diameter, our effective strength or gets lower. So this is the curve. This is going to be figure 5.9. This gives you the correction for different sizes and calculation of the value. So let's see what is the CS for a 5-inch rod. So I'm going to give you just a couple of minutes, just a quick break for you to solve this. So we do the same thing as we do before. We're going to pick the 5-inch diameter here, go up to this curve, and then go to the left side, and then read our CS from here. So again, we need to be careful of what is the resolution here. So you can look at this. This is 0.7. So each line will be like 7, 2, 4, 6, 8, 10. So this is corresponding to 0.02 in the size factor. So this is 0.7. So this would be 0.72. This would be 0.74. So you can basically report this as 0.73. So we're going to look at a few other considerations for the size factor. So since the testing is basically done in repeated and reversed bending, and the part basically rotates, that basically means that the entire section is on the outer fiber is subject to the high load. So if you have a different shape, so we are basically looking at the area which is subject to 95% of the load, which would be this area here. So if we do that, if you wanted to look at a non-circular shape or a circular shape in kind of like if a non-rotating shape, the 95% area changes. So not the entire outer fiber is subject to the full load. So we basically would refer to figure 5.10. So the A95 would correspond to 0.076 d squared, and then we equate this and then we find that the equivalent diameter for a non-rotating section is 0.37 d, and for a non-rotating rectangle this comes to 0.808 times the square root of the height times the width. For axial loading, regardless of size and shape, the CS is always taken to be 1. So this basically concludes our quick discussion on calculating the effective endurance strength of ferrous material. Thank you.